power of knowledge, the power of technology. This is you to the power of IBM. Find out how you can do your best work at ibm.com/you.
Get in touch with technology with TechStuff from HowStuffWorks.com.
Hey there and welcome to TechStuff. I am your host, Jonathan Strickland, and now I'm going to bring you the exciting conclusion about weather technology. Dylan has joined me for this episode. This was a show that we recorded all in one go, but it turned out to be too long for a single episode, so we've broken it up, and that means we are now going to join the podcast already in progress. We were able to gather a lot of information once we had those basic tools available to us. But what really pushed meteorology forward is when we could stop relying upon the data that we can gather here on the ground and supplement that with information from the atmosphere itself. And that brings us to weather balloons.
Weather balloons, more than just fodder for your Roswell conspiracies.
Right. It's swamp gas and weather balloons, and weather balloons do more than just act as a subplot in an X-Files episode, right?
Yes, they're very important.
Yeah, so they carry instrumentation that collects data about atmospheric conditions, and weather balloons have been around for a long time, but more recently they typically carry instruments called a radiosonde, which is a battery-powered device that can measure altitude, atmospheric pressure, temperature, humidity, wind speed. Sometimes there's a GPS element to it, so it can so people on the ground can track where the weather balloon is. Normally, you tether these devices. You don't just release a weather balloon and say "see ya," but sometimes you need to have that GPS element there too. And getting this information from the atmosphere is really important because it can tell you about how conditions may soon change on the ground. It's pretty interesting, actually, if you've ever had a chance to look at some of the data pulled from these, because you see how different conditions in the atmosphere are compared to what we experience here, including some pretty intense winds at higher altitudes. So we've got all this information being collected. And before we get into space, because that'll be the next step outward, I wanted to talk a little bit about what we do with all that data. One of the things we do is we create databases that have all this information, so that, let's say that we have a day with pretty nice weather. We collect all the information about that. What was the atmospheric pressure? What was the temperature? How much humidity was in the air? What was the wind speed? Were there any high or low pressure systems nearby? What kind of front had just moved through? All this sort of information. We feed it all into a database. Collecting that over and over and over again allows us to build a better virtual understanding of how weather works, right? And we can supplement that with more information as we learn more about the weather. Then we would end up using that to help us make some predictions about how weather might be in the future. And to do that, really, we use computer models. Typically, we would build what is called a numerical weather prediction model, the NWP. So this is really a model that's made up of a bunch of different calculations that take all of the different variables into account and tell you, based upon all the variables available to us, here's what it looks like the weather is going to be like in X amount of time, right? So whenever we're talking about forecasts, obviously we have to worry about what are the current conditions and how far out are we trying to predict the weather.
And on TV, you might see 5 or 7 or even these days sometimes 10.
Yeah, like if you go to weather.com, they have a 10-day forecast, which I always think is hilarious. And the reason I think it's hilarious is here's how those predictions work. You take all the information available to you. You run it through your computer model, which factors in these different variables and gives you sort of a percentage of probability of what your weather is going to be like in the next, let's say, hour. What if you want to look 2 hours ahead? Well, then what they do is they take the prediction that they made for an hour from now and extrapolate from there, saying, well, if in fact the weather is what we think it's going to be like in an hour, this is what it should look like 2 hours from now. Well, if you want to look at 3 hours from now, well, let's take what the results were for 2 hours from now and extrapolate again, and that's what we think it's going to be 3 hours from now. Mm-hmm. Extend that out to 10 days.
Yeah, and it's going to become less and less reliable.
Yes, because you're basing your predictions upon the results of a previous set of predictions, not upon a previous set of actual conditions, right? So when you're tracing it all the way back and your starting point is right now, well, clearly the further out we look, the more unreliable the information is going to be. The more likely some other variable that we have not anticipated will play a larger role or a smaller role, and that is going to affect the overall outcome of the of what will actually happen. The forecast is the same, but the actual thing we experience might be very different. Mm-hmm. Which is why if you're planning a picnic and you've got 10 days out from it and you're looking at the weather and it says it's going to be absolutely perfect, don't bet the house on it, because that's not necessarily true. Not
to discredit numerical weather predictions, because a lot of science and time goes into it. But it's still, the way that I see modern meteorology is that over time we have continually built upon basically what our ancestors did, and just it's gotten more scientific. We've gotten better instruments. But it's still looking for patterns.
Yeah, exactly. Right. So you might look at the patterns of when all of these conditions are in play. Out of the last 100 times that happened, this is how the weather turned out, and we're going to break it down. So maybe 80 days out of those 100 days where the conditions were similar to today's, it didn't rain at all. It was perfectly sunny. So 80 out of 100, it was lovely. The other 20 days, it rained, and it was just steady rain, and that's all there is to it. This is a super oversimplified version of what could happen. This is what would lead you to say there's a 20% chance of rain. Because you would say, all right, out of the last 100 times the weather was exactly like it is today, 20 of those times it rained. 80 of those times it did not. Therefore, there's a 20% chance that it will rain. That, again, is oversimplifying the way it works. Mm-hmm. But generally speaking, that's kind of how they come to those determinations. And in fact, there are ways of bolstering the NWP by using something called model output statistics, which is, I kind of just talked about a little bit. I'll just go ahead and touch on it right now. It's essentially doing what we were talking about, looking at a specific region and the specific outcomes of days that had similar conditions to the one you're looking at right now. And then you're kind of making an educated guess based upon a computer model and actual localized history.
I bet that cleared something up for a lot of people.
I sure hope so.
Because I've just kind of gone with it. I've just seen, 20% chance of rain, okay, and never really thought about what goes into determining that.
And I know that there's some people who had, when they saw 20% chance of rain, they thought it meant, it's going to rain over 20% of the forecast area. Which means that, that would be more like scattered showers. That's really what scattered showers means. When you hear scattered showers, it means that parts of the forecast area are expected to get rain, but it will not necessarily rain over the entire forecast area. Mm-hmm. But if you hear 20% chance of rain, it does not mean that 80% of the forecast area is going to be dry and the other 20% is going to be wet, nor does it mean it will rain for 20% of the day. In fact, that's part of the problem. A prediction of precipitation, the good old POP, the POP. So POP, that requires a time element to it as well. It doesn't mean anything without a time element. So if you say there's a 20% chance to rain, you also need to have an element of time attached to that to make it meaningful. So 20% chance to rain over the next 6 hours. Then all right, so it's not saying that it's going to be 20% chance to rain, or it's not going to rain 20% of the day, just that for the next 6 hours, there's a 20% chance it will be raining in the forecast area.
Hey, I'm Jack, host of the new comedic news and pop culture podcast, The Daily Zeitgeist from How Stuff Works. A little bit about me. I've listened to almost every episode of Stuff You Should Know and Stuff You Missed in History Class. I'm the co-founder and was the editor-in-chief of Cracked for the last 11 years. And our show's basically the day's news and pop culture filtered through a brain that contains all the information that entails.
And I'm Miles Gray, Jack's co-host, a former political operative and pop culture addict, like something I actually take medication for.
He does. And sometimes he's a bunch of different people, like Michael McDonald.
Tell him he's a stranger.
Japanese radio DJ.
皆さんおはようございます。マイルスです。
And Making a Murderer's Brendan Dassey.
Yeah. No.
Just a fair warning, guys, you're going to learn a lot, but some of the content can get a little edgy, so not for young ears, but trust us, it's all in good fun. So go to Apple Podcasts and listen and subscribe to The Daily Zeitgeist. It's really good, is our catchphrase. We're still working on it.
So I hope that demystifies some of it. Also, we can talk about Radar, one of my favorite things to talk about. Radar's awesome. Favorite character on MASH.
Me too.
Yeah. Well,
Yeah.
I think he's so adorable, right?
Yeah, it's hard not to feel for him.
And the fact that he can anticipate everything his commanding officer wants, and he can even say what the commanding officer is saying before the commanding officer has finished a sentence, is obviously a key part of that operation. But we're talking about actual radar, using radar to detect weather. You've probably heard Doppler radar when looking at a weather report. Like, well, let's look at the Doppler radar and see where this precipitation is moving in. Doppler radar for weather is different from Doppler radar used by, say, police officers who are trying to detect if you are speeding. Mm-hmm. The Doppler radar that meteorologists use actually shoots out radio waves in very short bursts called pulses. And then the radar listens for any echoing pulses coming back to the antenna. And the short pulses indicate not just the presence of something out there, but whether it's moving and which direction is it moving in. Is it moving toward the radar station or away from it?
If a Doppler radar receiver detects waves of a higher frequency, the precipitation particles are moving toward the radar.
Exactly.
And lower frequencies, they're moving away.
Yes, because what's happening is it's similar to a Doppler shift. And anyone who's ever heard a vehicle with a siren go past is familiar with this. It's a higher pitch as the vehicle is coming toward you and a lower pitch as it's moving away. What's actually happening is as that vehicle is moving towards you, the sound waves it's emitting are being compressed. Now, that compression creates a higher frequency, which means we detect a higher pitch. As the vehicle passes, those frequencies are elongated, which means a lower pitch. Same thing is true with the radar, except instead of it being a pitch, it's a radio frequency. So a higher frequency will tell you, yeah, something's coming towards you. And a lower frequency will tell you something's moving away from you. And also, the time between when the pulse goes out and when you detect it tells you the distance from the radar detection system and the precipitation. So you could even say there's a storm system that's 5 miles to the west. It's moving easterly at this speed because you've detected it through a series of pulses. If you have enough radar detection stations, you can even describe the shape of the weather system and talk about how some areas are more intense than others. You can get all of that information from this approach. And it's amazing how this thing works. First of all, it's super high power. These radar stations they're generating, or they're transmitting, I should say, at 450,000 watts. So your typical microwave oven is 1,000 watts.
Wow.
So you need 450 of those to equal one of these radar systems. So 450,000 watts, and the pulse lasts so short as to be unimaginable. It is 0.0000157 seconds long, or 1.57 times 10 to the minus 6 seconds.
So if you hear the weatherman on TV bragging about Doppler radar, there's a reason.
Yeah.
It's very impressive.
Yeah. I mean, you're sitting at a burst of radio signals at such a fraction of a second that it is, again, impossible to even imagine. Meanwhile, then it listens for a longer period, and by longer, I mean relatively longer. It's still a fraction of a second. It's 0.000999843 seconds. So it shoots out a pulse, listens for a little while, so it can detect when the pulse comes back and what frequency it's at, so it knows whether or not a body is moving toward it or away from it. And then it does it again. But that means with that amount of time and the comparatively large amount of time of listening, for every hour of operation, the radio or the radar antenna is only shooting out signals for 7 seconds out of an entire hour.
Wow.
That means for the 59 minutes, 53 seconds it is not sending out a signal, it is listening. So for almost a full hour, it's listening, and only for 7 seconds is it actively shooting out a signal.
Can you imagine having a conversation for someone who talks 7 seconds out of an hour?
It would, any conversation with me would last like a decade, and before you could get a word in edgewise. Yeah, it's pretty amazing, and you usually would have one of these stations shooting out these radio bursts at different angles of elevation. These are called elevation slices. And when you go through the entire range, you get what is called volume coverage pattern, or VCP. And that's what tells you what the activity is, not just at ground level, but up in the atmosphere as well.
Doppler radar can also detect tornadoes.
Yeah.
Yeah, if the particles switch from moving toward and then away over a small distance, there's a good chance it could be a tornado.
Yeah. We know a lot about those here in the Southeast too. We get a lot of tornadoes. Not as many as places in the, like in the Midwestern states, things like, Oklahoma and stuff. I mean, you guys get tornadoes even more frequently than we do. But we get them pretty seriously. Actually, this year hasn't been too bad.
No, but there was one in November.
Yeah, which is weird because typically we get them in the spring.
Yes.
Usually between March and June. That's kind of like our, let's play it easy.
Yeah, but you don't wish that on anybody, so.
No.
Yeah.
I have been through a close call with a tornado while wearing Renaissance Festival gear.
That sounds surreal.
That was my final day when I did my first run at the festival in 2001.
Wow.
Yeah, we had a really massive thunderstorm, and at one point someone said that there was a tornado watch, but not a tornado warning. Watch being that the conditions for a tornado forming are present. Mm-hmm. Warning being that a tornado has actually been spotted in the region, in case you were wondering. So now let's talk about satellites and meteorology. So the computers are really good for building out those models and giving us predictions. The Doppler radar is really good at tracking precipitation. What do weather satellites do? Well, they're keeping an eye on global weather patterns, but there are two different types of weather satellites, and they do this in different ways. So one is the geostationary weather satellite. Now, geostationary weather satellites maintain their relative position over a specific point on the Earth. They are at a very high orbit over the equator, and they're always looking at the same thing because their orbit is at the same speed as Earth's rotation. Not really the same speed, but relative speed, because it's able to stay in that same point over that part of the Earth. And so they have to be on an equatorial orbit, and they have to be at a particular altitude for this to work. It's great because it means they can keep an eye on a specific region. It's lousy because, one, they're really far away, so the instrumentation you have to put on these satellites has to be incredibly sophisticated in order to get good readings from that altitude. Plus, they have a limited view, right? They're always looking at one part of the Earth. They can't see anything else outside of that view.
Always geostationary.
Yep. So the other type you have are satellites that are in a polar orbit around the Earth. Polar orbits are interesting. So if you think of the Earth on its axis, the polar orbit is going parallel to the axis of the Earth. It's going perpendicular to the equator. So you would think of it as going from north to south and then south to north, because once it crosses the South Pole, you can only go north at that point. That's the only direction left to you. And it goes in that circle, which means These satellites get a full view of the entire Earth because the Earth is rotating while it's going in this orbit, north-south orbit. But it also means that you only get a look at the same part of the Earth twice in a 24-hour period. So it's once every 12 hours. You could always put another satellite up there, and that way you could get, put it on the opposite side of the Earth where it's in the same orbit, and then you get a look every 6 hours, just one from one satellite, and then 6 hours later, one from another satellite. But you also get to see everything on the planet. So there's your trade-off, is that you get a more comprehensive view, but you don't get a consistent view of any one part of the Earth with these kind of weather satellites. So a lot of weather services depend upon both.
Yeah, so it's good to have both.
Yeah. And typically they carry devices called radiometers, which usually have a small telescope or some sort of antenna, a scanning device of some sort, and one or more detectors that can pick up visible, infrared, or microwave radiation. And they use that to take measurements of the Earth and send that down to the planet's surface so that weather stations around the world can take that data and crunch it and figure out what the heck is going on out there when the frogs are raining from the sky, apart from amphibious assault. And all of those measurements are actually done through little electrical voltages, which then get digitized, so transformed into digital information before transmitted down to Earth, because, zapping electricity through space down to the planet is not the most efficient way of getting information across. And you certainly don't want to have a power cord stretch all the way there. That would just be such a pain.
Very inefficient.
Yeah. Also,
mess with aircraft patterns.
Yeah. And if you don't have geostationary orbit, it gets wrapped up around the planet pretty quickly. Yeah.
Deep in the back of your mind, you've always had the feeling that there's something strange about reality.
Well, there is.
Hi, I'm Robert Lamb.
And I'm Joe McCormick.
And we're the hosts of the science podcast, Stuff to Blow Your Mind.
What's it like to be possessed by fungus?
How did Neanderthals think?
Here's what we stand for: scientific skepticism, open-minded curiosity, and a love of the weird.
Because the world is weird, weirder than we imagine it, and we'll never understand it unless we're willing to go down to that place where our intuitions fail.
Could you create a god inside a computer?
Does the present moment actually exist?
On Stuff to Blow Your Mind, we put science on a collision course with philosophy, history, religion, mythology, and the worst space werewolf movies of all time.
We examine neurological quandaries, cosmic mysteries, evolutionary marvels, and our transhuman future, all in order to decipher the nature of our reality and expand the mind.
Subscribe to the Stuff to Blow Your Mind podcast wherever you get your podcasts.
And learn more at stufftoblowyourmind.com.
So, how do meteorologists do things like predict temperature, like predict highs and lows and that kind of stuff? For this, I went to a website that was written by a meteorologist named Jeff Habe. And boy howdy, did it suddenly dawn on me how much more complicated this was than I had even anticipated. But according to Habe, he looks at everything from thermal advection, wind speed, cloud cover, dew point, and the number of daylight hours expected for that region in order to come up with the prediction for the high temperature of the day and the low temperature of the day. So what the heck does all that mean? So thermal advection, what is that? That refers to the transportation of heat by a moving fluid. So typically the stuff that affects the advection include the strength of wind, so how hard is the wind blowing in that region, the temperature gradient between the warmer and colder areas. So if one area is warmer than the other, is it warmer by like a couple of degrees, or is it more significant than that? Is it like 10 degrees Fahrenheit? That would be a much larger gradient, right? And the angle between the wind direction and the temperature gradient. If that angle is more narrow, you're going to see a greater thermal advection, meaning you'll see more temperature changes moving into an area from a different region. So that's just advection.
That's a lot of play.
That's a lot of play. The other term you might be a little confused by, wind speed makes sense, cloud cover makes sense, daylight hours, all of that makes sense. But what about dew point? That refers to the temperature at which air must be cooled at constant barometric pressure for water vapor to condense. So that temperature, again, is dependent upon things like the actual air pressure, right? And so the dew point changes based upon those other factors as well. So all of those have to be taken into account before a meteorologist can forecast what the temperature is going to be the next day. This is why we're so happy to have those complicated computers now, because if you were to keep track of this yourself, you'd probably go bonkers. And then we have like the idea, the probability of precipitation, which we kind of talked about already. But generally speaking, there's some weather services that will only predict rainfall if it's expected to be over a certain amount, like 0.25 millimeters. If it's going to be less than 0.25 millimeters, it doesn't even register as rainfall in predictions. You would say there's a 0% chance or whatever, if that's what you think is going to be the accumulation. Some other ones are like, no, any rain at all counts. If it's one drop of rain, it rained in that region. So it really depends upon the service, but that we already talked about the percentages and what those mean. So hopefully that clears things up. And again, that kind of goes into that concept of model output statistics, where you correct for your predictions based upon past conditions for a particular region. All of this comes together to create the weather report that you see. So I think the real takeaway here is it's incredible the amount of schooling and expertise a meteorologist has to have in order to do his or her job properly.
Yes.
Right? Like, because you see how complicated this is, and you start to have an appreciation of, all right, they said it was a 60% chance of rain. I brought my umbrella. It never rained. Now you realize, well, when you're talking about a system this complicated and this unpredictable, something that can change dramatically just because something you did not anticipate happened, you start to appreciate more the challenge that they have to do their jobs properly. So give your meteorologist a hug and say thank you, because this stuff is hard.
Yeah, and if weather is the state of the atmosphere from day to day, and the atmosphere is super complex, it's my favorite analogy from our article on our website about meteorology is that the atmosphere is like a soup with too many cooks.
Yeah, yeah.
There's a lot at play, and so many different variables are working behind the scenes to give you a simple weather forecast that is easily digestible.
Yeah, this is also why when you hear about supercomputers running weather simulations, that's why you need a supercomputer, because of this too many cooks. I mean, it takes a lot to make a stew. I hope at least some of you are singing along now. But yeah, it really does explain why you need that massive amount of computing power just to do something that you would think would be fairly simple. You're thinking like, oh, it's like 6 or 7 factors. And then you realize, oh, wait, no, there's these other things that also have an effect. And in some cases, a measurable and meaningful effect, not just a potential effect. And it really does drive home that it's amazing we can have relatively accurate weather predictions in the first place. And also, it makes me kind of sad that I used to be on television with a local weather guy. He did a show at 5:30 in the morning, and I would show up on television and do a gadget segment with him. And it was great. He was very nice, and his ability to break down complicated concepts of weather in a way that was helpful to people so that they could plan their day was really amazing, especially when you start really thinking about all the things that come into play to make that, possible. So our hats are off to you meteorologists out there. Keep doing the good work. I look forward to learning more about, when we figure out even more details about the complexities of the atmosphere and perhaps are able to make even more accurate models. Maybe we will one day reach the Back to the Future 2 level where minute by minute it tells you what the weather is going to be. Of course, then I think they were actually suggesting that we would have weather control, which is a whole other thing.
That's opening a can of worms.
Yeah. I talked to Dylan that I said I had thought about doing a little discussion about weather control But obviously we've gone pretty long already. So what I will say about weather control is weather systems represent a huge amount of energy. And in order for us to affect or manufacture weather events on a large scale, we would have to be able to generate that amount of energy and pour it into the atmosphere in a way that actually does what we want it to do. And we're so far away from any of those things that it's absolutely unrealistic to think of weather control, even if you are a Cobra commander.
Going back to the beginning of this episode with that listener request for this, and that their father said that in the 60s that they felt like the weather report was just a joke. And you fast forward to now and how, maybe some days you grab an umbrella and you don't need it, but that it's, you can track major weather patterns and incoming storms, that we have a pretty good ability to track hurricanes and like flash floods and things like that. I can't imagine where I'll be in 40 or 50 years.
Yeah. The fact that we can get at least a heads up on stuff before it becomes critical to us is really important. I mean, Dylan, you probably remember it wasn't that long ago here in Atlanta when we had the snowpocalypse.
Yes.
And because it was one of those things where the initial weather report suggested that the weather was going to miss the city, and it didn't. That's an indication that, our predictions are not 100% accurate. They're not infallible. And it also taught us a valuable lesson, which is that even when you feel like there's a pretty good chance that you're going to miss out on that bad weather, it doesn't hurt to prepare, because the alternative is to spend 8 hours on 285.
Even if it is an inch of snow, because it's Atlanta.
Yeah. And because we don't have a system in place to deal with an inch of snow. And we got a lot of hills. Yeah. None of us have snow tires. Why would you? And
you let out the private and the public sector at the same time.
Yeah, that was particularly bad. I remember I actually stayed here, not here, but in our old office location. I stayed there pretty much through the full day because it was like, I'm going to take MARTA. I'm going to take the train. It's not going to be a big deal. It took me 3 hours to get home. Usually would take me 45 minutes. And I got online, got ready to complain, and then I started reading messages from my friends who were stuck in their cars and had been for 6 hours. I thought, okay, we're going to back away from the computer slowly.
Kids stuck in school buses overnight.
Yeah. So. Pretty rough stuff. So we're not perfect, but it is getting better, and it is pretty impressive to see the amount of information you can get. I find watching Doppler radar readouts to be fascinating. Like, I could have that open on my desk all day if I didn't have other stuff I needed to do. So, Dries, thank you so much for sending that request in. It was a lot of fun to kind of read up on it and to go over it. Dylan, thank you for joining me in the studio.
Thanks for having me.
Greatly appreciate it. If you guys have suggestions for future episodes of Tech Stuff, write me. Let me know what you think. I am actually reading those emails. For a while, Dylan, are you familiar with Outlook's clutter folder?
I am. I deleted mine.
You know what? That was a wise decision, Dylan, because it turned out that all of my listener mail for the last 5 months has been going to my Tech Stuff inbox clutter folder.
Oh, gosh.
So I discovered that last week, and I have since been going back and trying to answer as many of those as possible. I started foolishly with the most recent and started working my way back. So if you wrote me a few months ago and you're wondering why I never bothered to respond, it's because I haven't gotten to your email yet, but I'm still working my way through. But if you have a suggestion for a future episode, write me. I've been keeping track of those. We'll be covering them shortly. And also you can get in touch with me on Facebook or Twitter. The handle at both of those is TechStuffHSW. And I will talk to you again really soon.
For more on this and thousands of other topics, visit HowStuffWorks.com.
Atlanta, Georgia, 1979. One by one, kids are going missing, with no explanation. There was a real-life monster on the loose. But nearly 40 years later, this case has left more questions than answers. From the producers of Up and Vanished and How Stuff Works, we present an all-new podcast, Atlanta Monster. Subscribe to Atlanta Monster right now on Apple Podcasts and be the first to hear it on January 5th.